Hello, my name's Daniel. Welcome back to CS128 Honors, and today we'll be covering borrowing and references. So the goals for today are to recall a bit on ownership and have an overview of what we did last time, and we will be covering borrowing and dereferencing. We'll be covering some common errors that you may occur when using these, and some examples for how to use them in vectors. So, ownership review. Each value can only have one owner, and to change owners is called moving, and when a variable goes out of scope, it is dropped. You should have learned this last lecture. This is just a quick review so you remember what's going on. So, for transferring ownership, you have originally, let's say, an S1, a string, which has this data, and then you assign S2 to be S1. So you move the ownership of the data behind S1 to S2. But what if we don't want to move S1? What if we still want to have it, but we want to be able to access its data through another way? To solve this, we can do borrowing. Just like in C++, where you can assign a pointer to a variable, you can have a reference to a variable in Rust. This is done by taking the ampersand of the variable. Like here, ampersand string is a reference to a string. This, by default, is an immutable reference. On the next slide, we will be covering how to assign a mutable one. But what this immutable reference is it's like a pointer in C++. That it's a variable that all it does is tell you a variable that it's pointing to. So you can look at S1 from S. And you can access its values, like length here, through this interface. And when S is dropped here, only the pointer to S1 is dropped. S1 still exists, safe and sound, back in its original function. So a reference is created by taking an ampersand to a variable. It is done without taking the ownership of that variable, so both still exist. This is called borrowing, because the original owner still exists and has its data, but now the reference to the variable can also access that data. These are like references and pointers in C++. They refer to a value without needing to copy it. But in C++, you can have two pointers to the same object and then modify it in different places, which can cause problems when you expect to read something in one way in a function. And you can also have null pointers in C++. So you have to check for those every time. Rust offers a solution that essentially holds your hand through this process. Make sure it doesn't break during runtime, instead only during compile time so you know what's going wrong. So borrowing rules, at any time we can either have one mutable reference declared by ampersand mute, or an infinite number of immutable references, but we cannot have both of the same at the same time. A mutable reference must refer to a mutable variable, because we cannot change the variable unless it's mutable to begin with. A reference must always be valid, meaning that it must always refer to a variable that is currently in scope. We will talk about what happens later. And what if you want a pointer like in C++? Well, you can use a reference in an option. So you can have a functionality like a null pointer, but its checking is enforced by the compiler. Here's an example. Here you have the class variable, which is a string CS128H. We can pass a borrowed version and a reference to it to say hello borrow, which here you can see it prints hello CS128H. But since we didn't move the string to the function and didn't return it back, we only borrowed it. So class still lives inside of this function. This only references that variable called class. Then later here, class is moved outside of this main function into say hello back here. Of course, you could always pass it back, but here it's not passed back. So you can't use the variable class after you've used say hello here. Dereferencing is similar to C++, where using a star operator, you can either mutate the value for a mutable reference, just like you can in C++, or for more primitive data types like integers or floats, you can use the dereference on an immutable reference to copy, not clone, since this to clone you need to use the function itself and not copy. But let's look at the example on the left here. You have a mutable reference to x. Then here you dereference x, which is the number passed in here. You increment it by 1 and save it again. This dereference allows x itself to be changed rather than just the reference to x to be incremented by 1. And here, x would be 6 since we added 1 to 5. Here, though, since you have a more complex data type, like a string CS128H, you cannot dereference it directly, since it is currently in a reference. But what you can do is use clone if you want to have a copy of the value. But that is more expensive in many cases, so you need to work around this. So, when to dereference? You can dereference mutable references to primitive types. You can dereference when using an iterator, which we'll talk later in a vector example. You do not need a dereference when using bracket access. For example, when setting it like this, myvec idx equals this, you do not need to dereference like that. Or you do not need to call dereferencing when calling a string method, like .push string at the end of the normal string. You don't need to dereference the string. So, one problem that we may encounter often is an immutable borrow after a mutable borrow. What's the problem here? We only have one mutable borrow and we have infinite number of these borrows. That's allowed, right? The problem is that once you've borrowed this mutably, you're not allowed to use R1 and R2 again. Like for example, R1 and R2 here are used before R3, which is not allowed. It would give a big compilation error since you're not allowed to use an immutable reference after you've borrowed a mutable reference. This is a problem because you expect this data in the immutable reference not to change. But once you've changed it with this can have unintended side effects in your code if you don't know what the variable is supposed to be. So to fix it, you can change the order of how you borrow it. Here, you can print R1 and R2, then stop using them, and then declare another borrow, and then use that one. This way, these two references do not interfere with the mutable reference. A dangling reference, which I referred to earlier, is when you try to return a reference here to a string. For example, here, this case is a string, to a variable that doesn't exist. So here, you pass back the reference, but once this scope has been exited, the string s no longer exists. So this can't point to anything. But unlike a pointer in C++, you're not allowed to point to nothing. So this code will not compile. This can take there are some solutions to this, like in the Rust book, if you look up lifetimes, though we will not cover that in this course, especially not right now. The one way to do this is to just pass back the string directly, since if you're not going to use s anymore in this function, why not just return it to the previous function? So here, we cover an example of vector iteration. So let's say you have a vector here with numbers 1 through 12. To iterate mutably over it, you can use the built-in function v for the vector dot iter mut, which takes a mutable reference to each element in the list. Elem here is of type mutable reference to integer. And we can only do this since the vector itself is mutable. Here, as we mentioned earlier, we can dereference the mutable reference to an integer, modify it here, and then this equals will assign it and make it so that the vector in here has each element in here has changed to plus 2 times 128. This is an alternate way of doing it below that we have covered before, but this one's more advanced with references. Notice how here we do not have to take a mutable borrow, since doing this bracket notation infers that reference. So these are some methods that you can take. You can do any of these to access immutable or mutable borrows. And here, for example, just like we discussed the get before, this returns a reference to the element at I. Since if you just pass back the element at I, it'll no longer be in the vector, which is a problem. Here you just want to take a look at it. And here it'll pass back a mutable option. So, some announcements. Homework 4 has been released. It is due Friday, February 21st at 11:59 p.m., which is just over 8 days from now, I believe. Thank you for listening. How's lecture 6?